All right, so this is the first of a series of lectures on project management. One might initially want to know what is a project. All right, so a particular definition of a project is that it is a complex, non-routine, one-time effort limited by something, by time or by budget or resources or performance, that is designed to meet specific needs. Okay, that is a project. Um, Examples, things like this might include construction of a physics or chemistry department building, creating a new French dining experience, a variety of things. Many projects share the same characteristics on this. There is a clearly stated objective. There is a specific lifespan with a beginning and an end. All right, it may involve multiple departments, certainly involves multiple people working together. Many times a project is something that has never been done before, okay? And usually there are constraints of some sort with a time, cost, or performance set of requirements. So why manage a project? Why not just get into there and start working on it? Well, the reason why you might want to do this, all right, to pay attention to things like management of projects, is that and a lot of it is determined by the constraints. Okay, you want to in a project accomplish things within those constraints. So there's a balance trade-off. There's a trade-off between things like time, cost, and performance. If you've ever heard of the old adage, better, faster, cheaper, that's wrong. It doesn't happen. It's usually only two of those can you do. So there is always going to be a trade-off between these things, and that's another reason to manage a project. Probably one of the biggest things is unexpected things happen. Crazy stuff goes on. Murphy's Law. And so many people refer to risk planning or risk management as being the essence of project management. So when things start going wrong, the better that your project management is going, the more likely you'll still be able to succeed on these things. Projects generally require unique situations, and so you need it, and many times you don't know what you're doing with this, and this is very true in NASA. I mean, how do you actually? So next month we're going to be putting another spacecraft down on the surface of Mars. Well, there isn't any simulator that can do that. Okay, you can't really simulate that Mars environment, very well for things. So how do you actually assure that you can take a spacecraft traveling between planets and slow it down enough so that it softly lands on the surface of this other planet? There's a lot of management that goes into that kind of thing. Um, so that's something to keep in mind. Okay, structure. All right, when you go through a team, there's a variety of ways in which you can manage your structure. Um, Typically, a team will be composed of specialists, somebody who's going to focus on electronics, another guy focuses on software, a third on mechanical design, thermal, maybe there's a thermal engineer, on and on between that. And so coordinating those efforts between those different people is important, right? When you have a fully functional, well-run team, there's a lot of cohesion that goes in, but there's also kinds of problems that show up too. A team can become very insular and sort of reject outsiders or outside input, and you've got to be very careful about that kind of thing. And again, sort of emphasizing the team contract here in order to help define your rules of engagement. So a team has a life, and it has different stages that you go through in the life of that team. And these are called forming, storming, norming, performing, and adjourning, right? As you go through these things. So the first stage, when you're forming your team, this is when you get acquainted. You start figuring out how you're going to work together. You set your ground rules. What are the roles going, and how your interpersonal relationships are established. Storming is conflict. All right. This is, very usual that there is conflict in decision making. Group and project constraints are contested. There's all kinds of things which go on there. And again, your rules of engagement, your team contract can help you get through this storming stage. Once you get through that and you start normalizing your relationships and how your project is going to function, things get a little bit better, and you start getting a little bit more team cohesion. And at that point, you're at sort of peak efficiency in your team, where you really become very effective in performing on the project. Um, Once the project is done, and this is something which does happen. All right. Teams generally get very focused and very involved together in accomplishing a task. When that task is over, there can be emotional issues that go along with the end of the project and adjourning the team. So you do need to be aware that those things are normal, and that you do need to think about handling it. All right. So your team contract or your ground rules, there are things, and again, your faculty advisor will help you sort of work on this thing. But things that you need to think about when you do through that is how are you going to plan your project? Okay, who's going to be your project team leader or team manager? What specific roles are people going to have? What are their responsibilities? How are you going to track assignments? How are you going to make assignments? How are tasks identified and assigned to particular people? How are you going to track your changes in your documents? What kind of version control are you going to have? Um, when are you going to have meetings? How often are they going to have? How are they going to be run? What kind of agenda are you going to be putting out? Are you going to put out a agenda a day before, or or minutes after the meeting starts? That can make a difference, how you do it. So there's a lot of things that you need to think about in your team contract and your rules of engagement. Um, when you're conducting a meeting, make certain that it is regular, that you have it at regular times that everybody can meet at, that it's crisp, it's focused, and time constrained. I am usually in favor of more frequent, shorter meetings than infrequent, long meetings. You're much more effective to get things accomplished if you meet every day for 15 to 30 minutes, and you're focused on a particular or a couple of particular areas, rather than waiting every week and then having a 3-hour meeting where you discuss everything. So I would suggest frequent versus longer meetings. What's your team identity? All right. What's your shared vision? What are you going to do? What's your team name? Okay. How is that going to work? How are you guys going to work together? When you have problems, and you will have problems, you will have conflicts, and you will have problems, how are you going to resolve those problems? Right? Two people have decided that that one wants the payload to go in this direction and the other wants the payload to go in the other direction. How are you going to resolve that? Right? So these are things that you do need to talk about. All right. There are issues with project teams that you need to be aware of. Right? And if you aren't aware of these kinds of things, then you can get to poor decisions. For example, um, if the team becomes so arrogant that you become convinced that your decisions are infallible, that can lead to disaster real fast. Um, if you fail, and this is one of the reasons why, is that if you think that whatever decision that you made is perfect, then what's the point in examining alternate solutions or alternate issues? Okay. And so that can lead you to problems. Um, Stereotyping outsiders or issues or solutions. You can avoid considering other things that might make your project a little bit better. All right, and then even internal to the team, um, you need to make certain that your team is open, that all points of view are heard and expressed and discussed. So there are things that you do need to be aware of in a team. So a project, as we defined earlier, goes through specific phases, and these phases are common to every project. So your first phase in a project is the design phase. This is typically a paper study. This involves no hardware whatsoever, and where you're generally designing your initial concept of the project. That phase ends in the preliminary design review, where you define the particular characteristics of the project. Once you get through that phase, you then go through a development cycle where you're prototyping components of your experiment. Those components which are identified to be alternate designs. So you prototype a couple of these things to decide which one that you really want to go with. You are not building flight hardware during the development phase. You are prototyping your concepts. So things like, prototyping your payload mechanical structure, that's perfectly fine. You might look at several alternate ones and weigh them to decide which one it is. Obviously, sensor interfacing. There could be alternate kinds of signal conditioning circuits that you would, or sensors that you would be looking at. So those are all things that go into the development, and that phase terminates with the critical design review, and I didn't pull those things up, so sorry about that. All right, so that terminates in the critical design review. That critical design review, sometimes I call that the menu. Theoretically, I ought to be able to take the critical design review that you come up with and give it to a alternate team who has never heard of your payload before, and they ought to be able to build that payload based upon the CDR and give it back to you, and it would function as you define it to function. So I always sort of threaten every year to do that. Take all the CDR documents and mix them up and give them to different teams and let those teams, the original teams, sort of live with what gets made. I don't do that, but maybe one of these years, maybe this will be the year. I don't know. So anyway, the CDR is supposed to be a complete sort of design document that gives you a menu for how to fabricate your payload. Then you go through a fabrication. This is where you are building flight hardware in subsystems. You then integrate your subsystems together to build up your payload. And finally, you go through system testing that simulates the flight environment in terms of temperature, pressure, shock, other kinds of things that go through that, and your calibrations for your sensors, and that ends up with the flight readiness review. That flight readiness review should describe your payload as built and prove that that payload functions correctly. At that point, you would go through operations, so the actual balloon flight, gathering your flight data, and then analyzing your results. So those are the phases. So as I mentioned, the design phase is a paper study. Little or no hardware testing. on this. Your specific objective in the design phase is to identify your science goals and objectives and requirements. That's your initial part that you need to do. You then go through and based upon those that science background, the goals, objectives, and requirements, you go through a system level design that sort of looks at all the components and how they interrelate within your payload. System level design then generates into what's called the concept design, where you're providing a bit more details about how your payload should fit your requirements, and you're starting to identify what your parts and cost and availability and timeline is supposed to be to do this. This whole process, as I mentioned, ends up with the preliminary design review document. And in that design review, okay, well, this sort of shows you what the design process does. You go through, you come up with a design, I'm sorry, this is the development. This is after the PDR. So based upon your design, you then prototype your various components and then test those to determine which one is actually useful, and they'll make a decision as to how you go. And you would go through that cycle as many times as you need in order to finalize what your complete design would be looking like in there. You would normally probably, if you have long lead items that you would need to order months in advance, you would probably order these during this phase, during the development, to make certain that they're there for fabrication. And you would begin finalizing your pre-flight phases, as well as looking at your risk assessment for these things. You end up with what's called the CDR at that point. Finally, there's fabrication. So fabrication becomes a little bit more complex. You would order parts. There might be some training, like surface mount soldering perhaps, or other things. Those parts then get certified or qualified for assembly. You put those parts together in your sub-assemblies, you inspect, you do a thermal test, and if there's any issue, you work your assembly. And then finally, after you're done with all your subsystems, you can integrate everything back together again. That integration phase has, again, several different steps with it as well. First of all, make certain everything fits together, right? Then put it together, test it for however tests that you have identified what you need. If there's a problem, fix it, all right? And then you got to do that integration all over again, and until you actually have something that's fully functional at the end of that. Once you do that, you'll supposedly have a fully functioning payload. So that leads you into the system testing phase, all right? And there you're going to do a full functional test, make certain that all the components are actually working. You'll do a calibration of your sensors, and then you'll go through a specific set of tests, a thermal test, a pressure test, and a shock test. If at any point your payload fails one of those tests, you go back to the beginning. You fix it, and then you go back through the functional test, calibrations, and then you start over again. So, for example, if you pass the thermal test and the pressure test, but you do your shock test and your system doesn't work, okay, well, you better figure out what's wrong. Go back to your functional test, go back to your calibrations, and redo your thermal and pressure test, and then finally, hopefully, your fix will have fixed your shock test. So this is a sequence of operations, and you have to go through each of these tests with 100% success before you get to the end. After you get through these tests, you need to check your calibrations, make certain nothing has changed. And then finally, this is all input to your flight readiness review as you go through. Mission operations and data analysis, these are things that you need to take into account. Your mission operations plans includes things like how you're going to prepare your payload for flight, what's going to happen getting up to launch on it, what sort of flight profile requirements you need, what's your ground systems, how you're going to operate the system, how are you going to analyze your data after the flight, etc. If it is not written down, it did not happen. It doesn't matter how much you complain about this, that, or the other thing. If it is not written down, it didn't happen. Oh, Dr. Guzik, we did all the system tests. Oh, how come it isn't in your FRR? Oh, but we did it, blah, 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 blah. Nope, didn't happen. All right. If it's not written down, it didn't happen. This is an ancient wise saying. Right? One that's not as ancient, but it's still a wise saying. If you wrote it down, you agreed to do it, i.e. your team contract. You need to sign, each one of your team members needs to sign off on your team contract. You agreed to do it and conform to those rules. So those are two things that you need to be paying attention. Communication and documentation is key for a successful project. That's why we have you go through these processes with these documents. It enables you to track progress. It enables you to develop an agreement as to how you're going to proceed, and it assures that that two units can communicate with each other. So, for example, software and electronics. All right. Software needs to understand what is required out of the electronics in order to properly program the system. Likewise, the electronics has got to be able to communicate as to what their needs are and what are coming out of that. So there is things need to be written down like that interface. Your documentation provides the glue that stabilizes your project, right? Unifies that project and stabilizes it. It provides proof of performance, like for example, the FRR. You've written it down, you've gone through all the tests, you show your flight data, you show your test data, you have proven that it works. Finally, and this is most important, well, maybe not most important, but this is going to be something that is going to come up through the rest of your life, through your career, that reports and presentations document your performance, and they set the precedent for acknowledging your effort and or discoveries. There's a famous phrase for faculty, publish or perish, right? Faculty members at universities are regularly evaluated on how many papers that they publish in peer-reviewed journals, okay? That is in order to establish their performance and their discoveries. So this is something that you are going to do for the rest of your life, is this documentation. All right, so these reviews, let's talk a little bit about what these reviews are. So we've already talked about which ones you're going to do. We also provide you with templates that I'll talk about in a second, to split things up, to make it a little bit more manageable. We talk about a pre-PDR and a pre-CDR that happens before the PDR and before the CDR. This is roughly the schedule. We'll give you an exact schedule a little bit later on these things. Each team has to prepare the written documents for the review, the PDR, CDR, and FRR. Your institution may also require oral presentations of these things. And in fact, I would actually advise that the faculty advisors maintain sort of a review of the performance of the team with oral presentations frequently on this thing. Each of these reviews is somewhat different, and there's a different emphasis on these things. So the preliminary review, or the PDR, That objective is basically to look at the results from your design phase. The pre-PDR is going to be focused on your mission goal, your science background, your objectives, and requirements. All right, and then the PDR is going to build upon that to add your system design and your concept design, a preliminary risk analysis, preliminary risk assessment, and then that document goes to LACIS management, us, in order to review it. All right. So the splitting up. So these are the kinds of topics that would be in that review. And I've marked here the ones which are focused on the pre-PDR. And again, these templates are available through the ACES document page. You can download those documents immediately now, and I would really advise you to do so. And so you can see what these contents are. The CDR is the result of your development phase to tell us about the end of the development. And again, we split this up into a pre-PDR, a pre-CDR, and a CDR. The pre-CDR is focused mostly on your final system design and interface. And then adding to that is additional issues with the risk management, MODA, and a few other things like that. And again, here's the sort of split of the topics and the expectations about what we would want to see in the CDR. Notice here that this one here, resolving issues identified during the pre-PDR. These documents build upon each other. All right. So the pre-PDR leads into the PDR. The pre-PDR leads into the pre-CDR. The pre-CDR leads into the CDR, et cetera, et cetera. If you delay your early ones, the pre-PDR, or if you have so many problems that you need to redo it, you are going to be behind. All right. So you need to spend the effort up front in getting these things done and focused. Some of the harder things for student teams to do is to understand how to establish a requirement, how to establish a goal and objectives, and we'll get into those during the next sessions as to how that stuff works. But you need to keep up with these documents. Finally, the FRR, as I mentioned, is a sort of as-built document. It provides information about whether or not your payload functions as you claim that it was supposed to, and whether or not it's safe, whether or not it's possible to attach you onto the flight string in here. So the FRR, so for the FRR, there's going to be two things that you're going to be doing. One is going to be the document, which is again going to build upon all those previous documents. You keep on adding to your document to build up these sections. And as I say, it is not unusual for this FRR document to end up being 60, 70, 100 pages. Right? Not unusual at all with these kinds of things. You're also going to be doing a defense of this. When we get to the flight operations, you're going to be required to give a oral presentation on your FRR, and that will be at the Columbia Scientific Balloon Facility in Texas when we go there. Make certain that you understand. We take these documents very seriously this semester. So successful, i.e. passed, PDR, CDR, FRR documents, and the FRR oral presentation will determine whether or not you are allowed to attach to the flight vehicle. All right, period. That is what is going to happen. After you fly, you're still not done. All right. So typically during these flight operations, we devote a week at CSBF in Palestine, Texas. On Monday, we do the FRR presentations and prepare the flight vehicles for flight. Tuesday is the flight operations and recovery. And then after that, you have the rest of that Tuesday and Wednesday to read your data, do your flight analysis, and prepare your science report, which, if all goes well, your science report would be presented to the CSBF engineers and scientists Thursday morning. So you'll have roughly about 28 to 48 hours to get your data done. I would strongly recommend that you make certain that all of your ground analysis software and calibrations, et cetera, is ready to go before you leave your institution. All right. So here's the record schedule, just to reiterate this. So your PDR document is due February 22nd. Your CDR is due March 31st. Your FRR is due March 3rd. Note that all these documents are due on this date by 2200 Central Time. All right, so roughly 10 p.m. If it's 10:05 p.m., you're probably going to be behind the 8 ball in being able to prove that document had better be worth the extra 5 minutes. All right, is all I have to say. So it's very serious. The other thing about the reason why we are very insistent about these kinds of schedules is that that's the way NASA operates. All right. You have a schedule. There is a deadline. It isn't that, oh, well, my hamster died, NASA, and, therefore I couldn't get the flight requirement test done to you. So can we put off the launch for another week? No, the launch will still go. They'll just remove your payload from the launch. Okay. So the schedules are serious, the dates and the times are serious, and you need to make certain that you take this into account. All right, and then here's the schedule as it current stands. It says LACES 2020. It's actually 2021 flight schedule. So we'll have more about this as we go through the semester and define this. So